Good evening, everybody. It's my very great pleasure to chair tonight's inaugural lecture by Professor Philipp Koehn here, who holds a personal chair in machine translation here in the School of Informatics. I'm Leslie Yellowlees, for those of you who don't know who I am, and I'm Vice Principal and Head of the College of Science and Engineering. So Philipp is one of my boys, and I'm immensely proud of him and all you have achieved. Well done. So Philipp is the world's most renowned young researcher in statistical machine translation. I'm having to read this bit here because that's not my forte. And that's known as SMT, which I always knew as the buses, to those in the know, and in particular in the importance of phrasing as opposed to individual words. So Philipp was born in Germany, and we're especially delighted to welcome here tonight from Erlangen his father, Johannes. So very welcome indeed. It's always good to have a supporter like that. Philipp obtained his Master of Science in Computer Science from the University of Tennessee, and then his diploma in Computer Science from the University of Erlangen-Nuremberg. In 2003, he gained his PhD from the University of South California after submitting his thesis entitled Noun Phrase Translation. After a brief stint in MIT, he joined us here in Edinburgh in 2005 and quickly realized his potential, gaining his personal chair last summer. Philipp has published the seminal textbook, which is titled Statistical Machine Translation, not too surprising that, and consults for Systran and Asia Online, where he holds the post of chief scientist and which, according to Wikipedia, that's the fount of all my knowledge, he is a major shareholder. So other projects Philipp has been involved with are the Moses Machine Translation Decoder and EuroParl Corpus. On the basis of his publications, he is currently ranked third in the ACL anthology list of the most cited authors, so you've still a little more to do there. But let's hear about some of those publications and some of your work now. So it gives me great pleasure to ask you, Philipp, to give your inaugural lecture entitled Open Problems in Machine Translation. Philipp, please. Thank you.
Yeah, thank you very much for the kind introduction. So the advantage of machine translation is that it's a problem that everybody can understand very well. What if you come across this? There might be a handful of people in the room who know what that means. But if you run this through Google Translate, you get this. So, South China Sea Fleet Combat Patrol Farsi Training Formation on the 21st Stereoscopic Beach Landing. I like stereoscopic. I don't know what that means. So this is not that great. Let's try another language. Let's try French. I got that also today from the internet. And the translation starts out great. The receipt was simple. The austerity budget would restore confidence and this growth. It would balance the public accounts and the return of the activity. Good old British common sense. Thus spoke George Osborne, the peremptory and spirited Chancellor of the Exchequer. It does not happen. So far, actually pretty good. It does not happen is kind of wrong tense. Since coming to power in 2010, David Cameron, the relentless austerity policy London to conduct no more restored the growth it has cleared up the finances of the state. It gets a bit jumbled at the end, but it's basically fairly representative where machine translation is today. You understand the story, where previously it was all gibberish, funny Chinese symbols or French. And it might be useful for some purposes. I'll get to what is useful for at the very end of my talk again. The bulk of the talk, I want to talk about the problems we currently try to solve and some of the approaches we currently undertake to address them. So we actually have a very clear idea how we're going to do this. So this is kind of the grand master plan that machine translation had for a long time. So we have a source language, we have a target language, and maybe also have some concept of meaning that is beyond language called interlingua. So we start out simple. Let's just take the source words, translate them word by word, jumble them around maybe a bit, and have a target sentence. So that's a good idea. Maybe we should get a bit smarter and actually have some kind of analysis. So computational linguistics has learned something and has learned things like syntax and syntactic structure. So maybe you want to do a syntactic analysis first, then have a syntactic transfer and generation. And maybe you even want to go a step further and reach semantics. This is where things get a bit haywire because nobody knows what that really means. And the final step of interlingua, actually nobody has a very good plan because I've never seen actually an interlingua. But that's kind of where we want to progress in our research. So start simple and move up. The other big idea we have is that we want to learn these models from data. We need two types of data. One is what we call parallel text. So, for instance, Chinese paired with English, ideally sentence by sentence aligned, and run that through a statistical analysis and then have a translation model. And we also collect a lot of text in the target language to figure out what is actually fluent language, what makes sense. And that's our language model. Once we have these two mathematical models, we can then use a decoding algorithm to translate new sentences. So here is our, I have to have one formula at least in the talk. This is our goal. We want to find the best English sentences that maximizes the probability of all possible English sentences given a foreign sentence. So we have a foreign sentence given to us. We try out all English sentences, and we pick the one that our model likes best. This is what we want to return. Okay, so why is that a good plan? Let's go over a little bit the issues we have in translation and why this kind of strategy might fit it. So this is the most obvious. First problem, words are ambiguous. So you have two sentences here. He deposited money in a bank account with a high interest rate. And then you have a sentence, sitting on the bank of the Mississippi, a passing ship piqued his interest. In most languages, you would, if you translate these sentences into most languages, you would have different translations for bank and interest in these two cases. So how do we actually then find out which is the right translation to use? Obviously, looking at the context might be helpful. That's how we figured it out. I mean, we have a good sense what the first meaning of the word bank is and the second meaning of the bank is because we read the entire sentence, so we know what the whole sentence is about. So we should do something similar in our models. There is the phrase translation problem. Sometimes you can't just break things down into words. So it's raining cats and dogs. It's a popular sentence. And here's a possible German translation. Es schüttet aus Eimern, which literally means it pours from buckets. So here you can't just translate word by word. So you have to have larger units that you map. And how can we learn the translation of larger units and how do we deal with them? Then there's the issue of syntax. So here's another classic sentence that I stared at a lot from German. Sie behaupten, das behaupten Sie wenigstens. It's a good German sentence. It's fairly ambiguous. So das means this and the. Behaupten means claim. Sie could mean they or she, and wenigstens means at least. So to translate that, you have to convert the sentence, which is an object-verb-subject order, into subject-verb-object order. And you also have to resolve rather tricky syntactic ambiguities. For instance, that sie here should be they and not she. And the only way you can figure that out is by agreement with a verb in German. So here only the verb they is actually possible because she wouldn't agree with the verb. Okay, then we have semantic problems, and you already have one of the researchers popping up. I'll pop up everybody else, so they're not going to pick on you, Leon, who worked on this particular problem. So if you have this sentence, I saw the movie and it is good. If I translate that into German, in German all the nouns are gendered, so each noun is either male, female, or neutral. And if it's movie and I translate that into German, it would become film, and film is male. So suddenly you have to translate it in the male sense. And how do you do this? So that's a bit tricky. So you have to basically go through this entire chain. You need to figure out that it refers to movie. That's a tricky problem in itself. That's actually one of the hardest problems in the whole pipeline. You have to figure out what all these pronouns actually refer to. Then it gets easier because you know what you translate movie into, because you translate the same sentence, so you can look it up what you did, and you have to look up the gender of the translation film. So because it is a male gender, you know it has to be er in the translation. So we actually tried this a few times, and it's still an open problem. So we haven't really succeeded too far with this. Okay, another problem kind of along the same lines as this here. Whenever I visit my uncle and his daughters, I can't decide who is my favorite cousin. Cousin is one of these words. In German, you have to figure out what the gender is. So in English, you do this for siblings. You say, it's my brother or my sister. You don't just say, it's my sibling. But for cousins, for some reason, in English, you don't do it. But in German, you do. So is it a male cousin or a female cousin? You can see this is already very complex reasoning that has to happen here to get that right. So Bonnie Weber is interested in these semantic and discourse problems. Here's another problem that arises out of not having to translate words and sentences in isolation. So since you brought it up, I do not agree with you. So this is since in the sense of a contrast. Or since you brought it up, we have been working on it, which is in temporal sense. And again, in most languages, the since would have a different translation in these different sentences. So you have to determine which is the right discourse relationship here. So you have to figure out how all the sentences fit together and all the clauses fit together, and that's a hard problem. Finally, I want to throw this out. One of the biggest problems we face in building these systems and optimizing the systems is that we never know if we are right. So these are 10 translations that human translators produced from this Chinese. It's a headline of a story, but it doesn't really matter. It's a very short sentence, so it's remarkable. It's a very short sentence, and has 10 different people, independently of each other, produced translations. And they're all different. And this is not unusual. This is the total standard. Any sentence of 5 or 6 words, if you get a room full of people, they all somehow manage to come up with different translations. And they're probably also convinced that their translation is better than most of the other ones. So how can we ever know if you're right? So it's a bit of a concern. Okay, so that's kind of the transition to how we're going to address this. So the idea we had was we want to learn these things from data. So here is another popular word that I stumbled upon at some point. The German word Sicherheit has 3 main translations: security, safety, and certainty. And especially between security and safety, it's not quite clear what the difference in meaning really is, at least to me. Certainty has a clearly different kind of sense. So how should we translate it if we come across the word? So if we just come across the word, it might be good to know that the most frequent translation in a corpus that we collect, here the European Parliament, is security. So if we don't know anything else, we should go with security. We are probably more than 50% right. But it would help if we know a little bit more about the word, if we know where it occurs and what the surrounding words are. So if it's Sicherheitspolitik, then it's security policy. So then you should pick security. If it's Lebensmittelsicherheit, then it's food safety. So it's not food security. That also exists, but means something else. But it's not the common use of the word. And then there is Rechtssicherheit, and that's legal certainty. That's not legal safety. So this is kind of one of the key ideas. How can we actually figure out what the meaning of a word is? Well, we look at the surrounding words, and that helps a lot. Especially the directly surrounding words are actually very useful. Okay, another problem is that we have to produce text in the target language, and we probably have to piece something together, and we have to have various word choices. And especially for someone who learns English as a foreign language might be familiar with this, what is the right pronoun to choose? Is it a problem for translation? Is it a problem of translation? Is it a problem in translation? Maybe these all mean something different. It's all a bit hard to tell. If you just go by counts, it prefers a problem in translation. I don't know. Actually, I cheated. what it really prefers is a translation problem. That's just so much better than anything else. That avoids all these issues. Okay, here, I went through another example, and I thought there's a story, let's say there's a story in a foreign language, and there's a police and a demonstration. The police did something to disrupt, broke up, disperse, end, dissolve, stop, suppress, shut down, something to countervene somehow this demonstration. And the translation system might have all these choices. So I don't know which you prefer or which you think is the most native sounding. I'm not a native speaker, so I'm out of the game. I don't have to have an opinion on this. Any guesses? Join. Okay, so join. Okay, so the most frequent was stop the demonstration. Okay. So I hope you got a bit of a sense about the problems we face and the issues we have to deal with, and kind of a little bit the armory we have. So we have a lot of data we can learn something from, and we have some sense of linguistic and syntactic structure and meaning representation. These are things people worked on. So where are we now? One is we have a lot of data. So Hervé is someone who is crawling a lot of data for us all the time. So we have a lot of parallel data thanks to him. So at one point I made an estimation, and it's a totally cooked up number by me, so don't trust me on this. So the text you read in your lifetime might be 300 million words. This is kind of on a guess that maybe you spend an hour reading a book a day and then just multiplying that up over your lifetime. The amount of translated text we have is in the order of billions of words for some language pairs. So we have more translated text available as to train these systems than you will ever able to read. That's kind of stunning. And then the amount of English text that is on the internet is trillions of words. So this kind of keeps going, probably to MacArthur's seat and further, I don't know, maybe all the way to Norway. So these are massive amounts of resources. So we are very smart, and we know what language means, and we understand language, but computers can chew through much, much more data, more than we could actually ever grapple with. So we should be able to leverage this somehow. Already kind of mentioned in the introduction, the current workhorse in machine translation is the phrase-based model. It's a nice model. You can explain it on one slide. So the idea is you take just short sentence, and instead of translating words individually, you just break it up into somewhat small chunks. So you have your Spaß am, and so you have some larger fragments. You just map these source to target one-to-one, and you might do shuffle them. And that's pretty much it. So Nadir is working on, he sees our loyal opposition. He thinks this is not the best model, and he has a better model, and he's currently competing with us and maybe joining these efforts. What we also want is a language model. So this is kind of what I already demonstrated to you. Just looking up what has been said before. I mean, if something has been said before, it's probably more fluent than something that hasn't been said before. So the house is big, that's a good sentence. The house is XXL. Meaning-wise, it's there, but it's not something anybody would say. And how big is just terrible. So it helps both with word choice, because it finds words that just kind of fit nicely in the sentence, and it helps with word order. It's actually a very, very powerful mechanism. So the reason we can decipher foreign languages we don't understand very well is because we kind of grasp the meaning and then render the sentence. So we have, as humans, a very, very powerful language model that uses world knowledge and everything else. So machines are using much more simpler mechanism here, which just checks which words and sequence fit together. So if a sentence is a sequence of words, in the simplest case, in a bigram model, we just look, given that word, what's the next most likely following word? And if the words follow each other very, very nicely, we like the sentence. Typically, we don't use bigram models, we use 5-gram models. And you can also use syntactic structure in language models. But this is still kind of the main approach. So as I said, we're trying to move beyond this a bit. So we spent a lot of time over the last years on research on syntactic models. So here you can think of it as we don't translate just the individual words and as a string of words, but we want to look at the syntactic structure. We think, so there are various ways to do this. You could have syntactic structure on the source side, in the source language, or on the target side, in the target language. And there are different benefits and arguments why and where you want to have this structure. So on the source side, it might help you disambiguate certain things, maybe by knowing that there are certain syntactic relationships you would prefer reordering, not reordering at that point. Like you wouldn't want to reorder in the middle of a noun phrase and tear it completely apart. Or knowing that something is a verb or a noun might help you a bit. But we currently think it would be more helpful in the target language. So when we build a translation, that we not only build a nice string of words where all the words fit together nicely, but also nice syntactic structure. So we actually produce a sentence that is actually grammatically coherent, or at least we have some means to control that the output is grammatically coherent. So our favorite models right now are these string-to-tree models. We don't do too much about the source side syntax, but the target side syntax. So there are two researchers that work on this, Philipp Williams and Maria Delia. And there has been much progress. So this is kind of a field that is, a lot of problems have to be resolved and addressed, and things have to be tried out. There are many open questions. For instance, starting with when we ask linguists what syntactic structure is, they give us 10 different answers, and they change their mind every 5 years. So the examples that I showed you earlier, phrase structure, that's one way to do it. Here in Edinburgh, people like CCG, categorical grammar. There's dependency. Maybe you should just use dependency grammars and not these phrase labels at all. So there's a lot of unresolved questions. Once you actually agree that this is your syntactic structure and annotation you want to deal with, what kind of rules do you want to extract? How big have to be the rules? Do you want small rules? How do you handle actually the restructuring in rules? Already said syntax on source, target, or both. And how much do you constrain your whole machine translation pipeline by this new idea of syntax? Do you only produce sentences that have syntactic structure, or can you just say, I can ditch it whenever I want because I can't figure it out with the syntactic structure? So one approach that Philipp Williams has been developing also takes ideas from unification grammar. If you translate into languages with rich morphology, you actually need much richer annotated trees. You need to know what the gender of noun phrases are. You need to know if something is singular or plural, and so on. And if you pack all this information just naively into these labels, it makes them much more complex, and then the rules get more sparse and nothing works anymore. So the idea here was to separate some of the features of the grammar into feature structures and handle them with agreement and constraints instead of inside the grammar rules. So good question is, why do we actually do all this so complicated? Why do we build these syntactic structures? Why don't we do something similar, simple, take the source sentence, parse it, reorder it so we know it's in the target side order, and don't kind of try to build trees while we translate. Maybe we want to use syntax as features. So if you have a translation where something that was originally a noun phrase in the source is then a noun phrase in the target, yeah, it's probably good, but it doesn't have to be, but it's probably a good thing. So we give a bonus to those kind of translations. So we don't have to actually build all these complex structures. We could just use kind of these syntactic properties somewhere else. So our standard approach currently for German-English translation does exactly that. We know German, the verb is kind of at random places. So we parse the sentence, put the verb in the right place where it belongs after the subject, as it is in English. And then we translate. So don't let the system figure it out. I can write 5 rules that explain how the verb should be ordered. So why shouldn't I just write these 5 rules and don't let the learning algorithms do all the heavy lifting. So that works, unfortunately, surprisingly well, and we have been doing it for 6-7 years, and it's one of these things, but we haven't really beaten it yet. Okay, just want to throw that out. So there are some people who think about semantics and translation. So a couple of people here in Edinburgh were also visiting University of Southern California last summer, where they suddenly come up with these things. So these are semantic representations. So this means the boy wants the girl to love him. So you have the boy occurring twice. So this, you kind of see how this represents this kind of co-reference nicely by having the same entity, B, which is explained once as boy, as agent of the wanting, but also as the patient of the loving, so it occurring twice. Once you start going down the road, you never know where to stop and how much you should abstract things away. And it's a very preliminary stage of research. So there's no working system that really does that to any degree of quality. Okay, so this is more the linguistic-y part, or how we build the models. Having all these models is nice, but we actually also need to train the models and use the models. So let's start with a phrase-based model. So we want to translate a sentence. Here, geht ja nicht nach Hause, German sentence, but casual sentence. So we have all great models that tell us for all the input words and phrases what are the possible translations. And I'm just showing the tip of the iceberg here. So it just shows the top 5 translations for each input word and input phrase, for which we have something. We have sometimes thousands of translations. We usually don't go completely insane. We cut it off at 50 or 100. But you can kind of see what the computer suddenly has to face. So it has to pick the right translations and put them in the right order. So this is a huge search problem. So there are a lot of things to explore. And the search kind of looks like this. So you have this kind of the compressed phrase table up there. So you start at the beginning and say, okay, I haven't translated anything yet. So I kind of built this little data structure we call a hypothesis that says I haven't translated anything yet. So this means all these empty boxes, none of the source words are translated and haven't really produced anything either. And then I say, okay, let's translate the second word as R. Okay, so second word is marked off. I'm not going to translate the second word again. And press R. But I also have other choices. You can translate the first word as he or the first word as it. All these things. Okay, pretty much any of these lines or translation options that are given to me there, I can try out. After that, well, I limited some of them because I can't translate the same word twice, but I still have a lot of choices. So this, if I just draw this up naively, it explodes exponentially, which is generally bad news. But if we actually would succeed with this, we would then find from all these things at the end, all the complete hypothesis that translated all the words, we could pick the one that our model thinks is the best. So our model gives probabilities to all these things, all these different hypotheses. And one of them it likes the most, and then we can just backtrack and say, oh, here's a translation. He does not go home. So the process that was shown here suggests that it's exponential. It's been proven to be NP-complete, so we don't know if it's exponential, but it's definitely not nice. So you can do something with dynamic programming. If you know there are 2 different ways to translate the first 3 words, maybe as a big phrase translation or all the words separately, and you get exactly the same result. You have the same 3 words in the output. You don't have to now explore this twice. You can just say we are at the same point, so we can unify these 2 paths. And you can do some other tricks to make it more efficient. But basically, that buys you something, but it doesn't really resolve the problem. You just have to do some pruning. You just have to say, after 3 words, this translation just looks bad. I don't know, maybe something magical happens at the end and all the problems get resolved. But if I take my chances, I would throw it away. So the decoder might not find the model best translation. It's not guaranteed to find any good translation at all, but it's not even guaranteed to find the best translation according to the model. Typically, when we run these models, we limit the amount of reordering, which is a pretty heavy restriction on computational complexity. And then the whole thing becomes actually linear with a sentence length. So if you have a 30-word sentence, it takes twice as much as a 15-word sentence. Okay, next problem. We want to build syntax models because the linguists tell us we're stupid not to care about syntax. So here, German sentence, Sie will eine Tasse Kaffee trinken. And we built a parse tree. It's really just like parsing. So if you know syntactic parsing, that's what we do, except we parse and translate at the same time. So we might build some kind of low-level spans where we translate individual words. And then we also have bigger rules that do, again, translation and reordering at the same time and build up structure. So this is the rule where it says eine Tasse noun becomes, in English, a cup of noun. And the noun could be anything. So this rule can be applied to any noun, but it's a nice rule and it fits together nicely. Here's the rule that does all the difficult German stuff, where literally she wants a cup coffee drink. That's how Germans talk. So if you translate that into English, you have to reorder it. She wants to drink a cup of coffee. So you have to move all kinds of things around. The rule tells you, yes, you're going to pick up a verb phrase and a noun phrase, but you're also going to swap them around in their order. So this is a nice synchronous context-free grammar rule that does reordering and translation. And at the end, you just have to basically add the she, and then you have a full sentence. So theoretically, this is actually a much simpler decoding algorithm because it's polynomial, because you build these contiguous spans, and there are only n squared, many of them, that you have to build. So it should be simpler, but we can't use as many tricks with dynamic programming as we did in the phrase-based model. We are really hurt by having two types of models. One's the syntactic structure, where we build up spans, and then we still want to use our n-gram language model because it's really, really useful, and that sees things as strings of words. So when you build a span, you can't just say, this is the best possible translation for the span, so I'll stick with this. This is the best way to produce a noun phrase, because you don't know what the surrounding words are, and the surrounding words might tell you then afterwards, this is actually looks good, but it doesn't fit with anything else in the sentence. So in practice, this is much slower than the phrase-based models, to this great suffering of everybody working on this. Suddenly the experiments take a week and not overnight, and then it stops being fun. It's typically also super linear in sentence length. So the longer the sentence, it doesn't just linearly get slower. It gets slower and slower. It gets dramatically more slow. So often you run the decoder. It translated all the sentences except for one that has 137 words. And then you wait and you wait and you wait, and your whole great multi-threaded setup kind of comes to a grind, and everybody waits on this one sentence. So how to do efficient decoding here is still an open research problem. Generally, I can still use the buzzword big data. So this is a big data problem, as I hopefully showed you earlier. So we need to deal with all the issues in big data. So there's Ken Heafield, who actually also worked on syntactic decoding earlier, and Miles Osborne, who care a lot about these things. So how do you deal with having all this data? Well, first of all, you're going to optimize your data structure so you don't waste any bit anywhere. If you have to store 1 trillion words, you have to be really smart about this. So you have to have efficient data structure to deal with this. There's the idea by Miles Osborne and his former student David Talbot, who says, let's just make mistakes. And if you allow ourselves to make mistakes and do random decisions, we might get away with less memory. So he built these randomized data structures that were developed here as a PhD and are now standard use, for instance, by Google. And the other idea is to use distributed systems. So if you really think about it, 1 trillion words, you need terabytes to store that. That's not going to fit on one machine, at least not the machines we can buy. So why don't you distribute the language model over 100 machines? And this is actually what Google does. So you suddenly have your language model distributed over 100 machines. You have a decoding algorithm spread out over various machines, and you have to kind of coordinate all that. You have to rethink your algorithms to make them actually not constantly wait on network delay and all this. So there's some serious problems there. Okay, now I want to turn to finally to the training part of this. So I talked about statistical models. And obviously, there are a lot of numbers. So where do we get all these numbers from? So where do you get all the probabilities from, and language model probabilities and all that? So we think we'd work with language, but if you look closely, it's all numbers. So we really want to figure out what all these numbers are. So that's one way to look at it. So we might have multiple components in our system. So a translation model that tells us this is a good translation of that word. So that's something useful to have in your translation. And we have a language model that says, yeah, these two words go together well. We also have things like reordering model that say it's more likely that you reorder the sentence at this point than at a different point, and various other things. We have simple things like just counting how many words you produce, or how many phrases you used, how many rules you applied, and so on and so on. So one problem is to give these things weight. So what should I trust more? I mean, it's very easy to make the trade-off with the language model and translation model. Do I want to produce a translation that is as faithful as possible to the source? Or do I want to produce a translation that just sounds right? So you can overdo it in both ways. So if you just want a translation that sounds right, just pick a random English sentence from, the newspaper, and it probably sounds right. It's just not a very good translation of anything. Or you can also overdo it on the translation model by just really producing a literal translation, and it's just not good language in the target language. So we need to balance these things. We need to weight all these different components. So translation model, if you look inside these boxes, you also have to pick all these other numbers. So what's a good translation for house? Is cars a good translation? Maybe 35% probability, and so on. So this whole statistical machine translation craze started with models developed at IBM in the late 80s, where they first started out using the Bayes rule, which tells you that you can reformulate this original optimization problem we had of finding the best English translation given a foreign sentence into the reformulated translation probability and the probability of English sentences in general, of this English sentence by itself. So this is a mathematical justification to use a language model and a translation model. The translation model is now flipped around, but that shouldn't matter too much. Then you have to do a little bit more. So you can't just say, given the source sentence, what is the possible translation for the target sentence, because you might never have seen the source sentence before. So in the original models, this was all broken up into words. So you have to explain each English word somehow. Each English word, EI, is aligned to a foreign word, and you have to find then the probability that this English word is produced by the foreign word, and you go through all the English words. So this is a nice kind of mathematically sound development of this model. So you kind of do some mathematical reformulations. You throw in some independence assumptions here and there. So the words are the probability that a word gets translated in a certain way only depends on the source word, not on all the other words in the source sentence, and so on. And then we can do, if you have a nice mathematical model like this, we can just apply it to the data, and based on the counts we find in the data, we estimate our probabilities. And we use the EM algorithm to resolve some missing information in our data, for instance, the word alignment that has to come from somewhere. So if we have all these different model components, people quickly found out we can give them weights. That's not really mathematically justified in any clear way anymore, but it works, so we do it. So maybe you should give the language model twice the weight than we give the translation model. So now we kind of moved away from this generative story in these IBM models to log linear models, because if you take the log of it, it's just a linear formulation. So that now leads us to the problem, how do we give all these weights out? So each of the components that we have here has to be given a weight. And we do this by setting aside some tuning set. So we have a couple of thousand sentences that we need to translate, and we try to do as best as possible to translate them. So we try different weight settings. With each weight settings, we get different translations. We can check if these translations are good. And then we try another weight setting. If the translations get better, we kind of keep going that way. So here's kind of how you can visualize this. So you have your model. It produces an best list of possible translations. We look at these translations in the best list and say the first one is really terrible, that's why it's red. The second one is okay. The third one is good, I like the third one. And the fourth one, so how can I fiddle with these weights that the good ones come up to the top? And once I've done that, maybe I want to run the decoder again, because if I actually run the decoder with these weights, it might produce completely different translations. So the in-best list is just a snapshot of what it produces. So I'm not going to go through the algorithm, but this is the idea of the MERT algorithm, where it does this and it optimizes one parameter at a time and leaving the other one fixed, and it does some optimization. This is still something people use a lot. I want to dwell a little bit on what we have now done. So we started out with this IBM models where we talked about probabilities, and I've seen this word 5 times, 4 times it was translated this way, therefore the translation probability is 80%. So this kind of worldview, and now more machine learning, discriminative training kind of worldview where we just care about the outcome. So yes, this word has been translated 5 times and 4 times this way, therefore the probability is 80%. But if I set this number to 76%, maybe I get better translations out. So if I can have some kind of machine learning mechanism that tells us 80% is not good, do 76%, we are happy to say 76%, even we can't really explain it why. So originally you have this generative model where you kind of had a mathematical derivation to break things up to steps. Each step is modeled by a probability distribution, and we just basically use counts to do this. Then we use, but now instead we use discriminative training, we think everything is features. Translation probabilities are features. N-gram language model probabilities are features. So, so originally we looked at the translated corpus and came up with different rules, so translation rules, how a word gets translated to another word. So we have millions of these rules. How does the word the get translated? How does the word the of get translated? And we set all these by just looking at the corpus. Now we have this iterative invest list that we try to use to optimize directly translation performance on a held out set. These MERT algorithms unfortunately only work for a handful of parameters. And the holy grail is to optimize all these millions of numbers we have in these models by going over the search space and really seeing what really works with the decoding algorithm. So one idea that goes in this direction is the Perceptron algorithm. It has a very simple idea. I look at the translation I currently produce. I look at the translation I should have produced. I look at the features that are in the translation that I should have produced, and those are the good features. And the translation that I currently have produced, these are if they don't match, bad features, so I knock them down. Unfortunately, it's complicated. So if Hessler is working on this stuff, so we already had illustrated that there is no single correct translation for input sentence. So whenever you have a human produce a reference translation that you try to match, you might not get it. You might get something similar that might even be better than what a human produced, but you optimize against the wrong thing. The correct translation that you try to reach might not even be producible by your model. There's a big risk of overfitting your model to the training data that you have and trying to scale this up. Say I want to optimize millions of parameters by translating millions of sentences. That's going to get hairy. So this is work in progress, but we're making progress here. There are other issues in learning. So I said there's parallel data, there's monolingual data, there's different ways how you can use it. There's also this concept of comparable data. If you look at Wikipedia, there are a lot of stories that are translated, but they're not really translated. You have one news article about, University of Edinburgh in English, and then you have a Wikipedia page about University of Edinburgh in German, and you try to learn something from that too, but they're not translations. How do you deal with this? There's this issue of domain adaptation that you get a lot of parallel text and translated text, but it's usually out of domain. So finally, to wrap things up, the question you might have already wondered since the beginning, since all our translations are terrible, what's the point? So how good is all this? This is actually a common question. Someone comes in, so how good is machine translation? Okay, I'm not going to give you a number. I'm first going to tell you what it can be used for. So there's Google Translate, which we call assimilation. So the reader wants to find something out. What's the news in China today? I go look at the Chinese news agency's webpage, translate it into English. I know what the news in China is. I kind of get the headlines of the stories. I don't get all the details, but I kind of know what it's about. If I don't know how to fix my computer, but there's a help page in Finnish that explains it nicely, I translate into English. It might be jumbled English, but if I can fix my computer afterwards, I'm happy. The other one is to use it in handheld devices or the multilingual chat rooms. There's also tolerance for error, because if something goes wrong, you can always ask follow-up questions. It's like, what did you mean by that? And the third one is dissemination. So this is kind of the hard task. If you really want to publish if you want to sell refrigerators all over Europe, you have to have the product manual translated into all the European languages, so you need an Estonian user guide to your refrigerator. And this has to be high quality and needs to be done by humans. So if you take a bit of a broader view, this is a scale that was proposed by DARPA at some point. So if you look at H-star, it's basically the number of words that are wrong. So if it's perfect, 10% words wrong, 20% of words wrong. Maybe these are categories. So what does that mean? If you have 0% error, you can, there's no difference between translation, between the languages. If it's 5% errors, you might still be able to publish it because it's just here and there something wrong. There's a certain threshold where it becomes more productive for a human translator to post-edit the output of a machine translation system than to translate from scratch. So I kind of say maybe 15%. And then there's levels of gisting, maybe you want to use machine translation in some information retrieval, information extraction kind of scenario. Maybe you don't need to translate everything. If you get the information once right from one of the documents, you're happy. You don't have to get it right in all the documents. So there might be various levels where this is useful. So where are we currently? I'm just randomly placed these things, somewhat informed. So for instance, French English, as I showed you earlier, that's actually pretty good. So it's definitely a language pair where post-editing machine translation output is much faster than translating from scratch, if you have enough data in the domain that you care about. But English Czech, English German, it gets worse. So finally, one of the applications we work on, and I could give a whole talk about it, is how do you actually do this? How do you help human translators? You just could give human translators the output of an MT system and saying, fix it up. Or you can come up with something smarter. So Kara and Christian work on these two projects that we have here. So the idea is here, this is the sentence you have to translate. You already translated this, and now the system proposes this word. Okay, there's not much translation going on, but I had to fit something that fits on the screen. So how can you do this? So this is kind of like this autocomplete function. Maybe that's more useful than post-editing MT. There's ideas about confidence measures. Can you figure out which part of the translations are wrong, and so on and so on. Okay, finally, all the systems we develop, you can try them out yourself. We have a system called Moses that Hugh has started as a grad student here, and he can't get rid of, and he's still developing and improving it and fixing it. And he came back to Edinburgh to say, I want to fix Moses. It's still not where it is. So it's open source. You can try it out. It's widely used in academia and even by companies everywhere. So translation companies currently pick this up quite a lot. And that's it. Thank you very much.
Thank you. That was a wonderful talk. Questions? Yes, please. Could you wait for the microphone just so we can pick it up?
Yeah. Okay. I'll try and bring in the human part of this maybe a bit more. I mean, is the goal of machine translation to optimize the sort of knowledge transfer and information transfer, and therefore have a sort of cleaned up version, maybe a bit more generic? I mean, you can have your 10 versions of a sentence, but probably one of those is faster to read and process. And does that make it better because of it being easier to read and so on? Or do you want to capture the individual side of language? So the style, the personality, even in some of the errors that producers may produce, do you carry them over?
So that's a very broad question. I think what you try to produce depends a lot on why you're doing the translation. So I already said the tension between translation model and language model. So if I translate a web page that tells me how to fix the computer, I don't need beautiful English. I don't want any mistakes in it. So if there's no way to translate this finished sentence in a nice, fluent English, give me a jobble translation that doesn't make any mistakes. I don't want to have a translation that says, there's no word for that in English, let's throw it out. It sounds so much nicer if I throw away half of the words. So it depends a lot on the application. If like the objective that you said, a sentence that reads nicely and is easy to read and easy to consume, that might be one objective, but it's not necessarily.
And so it's easy enough just to tweak Moses to go one way or the other.
Yeah, so it's kind of a very clear trade-off between those two things.
Can I ask you, which is the most, I mean, you've concentrated on German and some French in there and English. What's one of the more difficult pairs?
So the easy ones are French and Spanish.
Right.
And then German is surprisingly difficult. I mean, given that's a European language and supposedly related to English, it's surprisingly difficult. And then if you go to Chinese, Japanese is also a real tricky one because everything is reordered compared to English. You have to restructure the whole sentence. Generally, there are languages that just don't have enough information. So Chinese doesn't have determiners, doesn't have plurals, doesn't have tenses. So if you have a Chinese sentence and you translate it into English, suddenly you have to figure out, is this in plural or not? Is this in past tense or present tense? So those things make things tricky. So yeah, the hardest ones are Japanese, Chinese.
And what about Chinese to German?
Yeah, that's not going to get easier. And we also don't have any data for that. So that's another thing. We have a lot of data paired with English, but not with other languages.
Thank you. Yes, please.
Hey, well, maybe I should already know this, but are there lots of companies that are out there doing translations and actually, making a profit and things like that, or is it something that we just do at universities?
Yeah, that's a good question. So nobody wants to pay for crappy machine translation, and you can get crappy machine translation for free from Google on the web. So the market for machine translation technology is not all that great. There are a lot of users of it. So the real money, that's why maybe the last slide about human translators. The real money is in human translation. So there's billions of dollars each year, pounds, whatever, spent every year on translation, on human translation, while maybe the market for machine translation is 100 million. So the money is really in getting really high accurate translations. So the angle for us to get in, that's why we want to do computer-aided translation, is if you can increase the productivity of human translators, that's where money is to be made.
How long is it going to take to get to human?
To human, not in my lifetime. That's why I have job security and.
Does he?
Don't have to rename my chair anytime soon. So.
Thank you.
Given this goes back to the question of which are the difficult pairs. Given what you said that an awful lot of the pairs are going to involve English, what are the chances that you're going to come up with a general approach to machine translation that's really an approach to translating from something to English or vice versa?
So we have a general approach. It just doesn't work very well. So this phrase-based approach doesn't really assume anything about language. It just says, I'm going to map some words, shuffle them around randomly, and whatever the language model likes, I'm going to output. Once you get into the intricacies of all the language pairs, you come across things like word order. Is word order very different? Is word order just very differently structured? Does it have a lot of morphology? On the source side, that's a problem because suddenly you haven't seen all these words yet. There's German that likes to build big words, and you have to split out all these compounds. On the target side, morphology is a big problem because suddenly you have to get all the inflections right, and you might not even have enough information, like the Chinese-English tense issue. So I think we're kind of in the stage right now where you kind of look at different language pairs, and suddenly things don't work, and we try to optimize things for particular language pairs, and maybe 5 years down the road, we can learn some general conclusions.
Can I ask Dave Robertson, who is Head of Informatics, to come and give the vote of thanks, please? Thank you.
Yes, well, thanks, Philip, for the talk. I mean, this particular talk was actually a particularly modest talk, and one that kind of strikes a chord with me because I'm old enough to remember the sort of talk that people would have given 25 years ago on this topic, and when they'd answered the question, how long will it be before the technology can approach human performance? The answer would have been the same, but for different reasons. I mean, at that time, the answer would have been not in my lifetime, because they had not a clue what the performance of the technology might be. And it's completely different now, because your answer is couched in terms of a very deep understanding of what the technology is and what its boundaries are. And it's thanks to people like you doing the stuff that you do that we now know that. And so it's the same answer, but in some other sense, it's a completely different answer. And of course, you're too modest to say, but for things like the Moses toolkit and so on, those things really are, benchmarks in the field. They are the standards by which other systems are judged. And so I think that's a mark not only of your maturity as a chair at Edinburgh, but of the field that you represent. So for all of those things, Philip, thank you very much.
This production is brought to you by the University of Edinburgh.